Okay. All right. So we are going to continue with our problem from yesterday when it shows up. So, right, what you just did on the board was that process of taking a guess for the form of your differential equation, solving, and seeing if we can find a pattern. So for our example from yesterday, we had the differential equation y double prime plus xy prime, or x squared y prime plus xy equals 0. We made the guess of the sum from n equals 0 to infinity of an x to the n. And what we found was a0 and a1 were arbitrary, a2 equaled 0, and then an plus 3 had this recursive pattern. So that's kind of where we got to yesterday. So our question for today is, can we find a pattern more generally for these? Okay, so I'm going to start potentially, if I can find it. Here it is. Okay. I am going to start with the multiples of 3. So if I'm looking at this an plus 3, right, what that kind of leads me to think is there's going to be like patterns for multiples of 3. So we start with a sub 0, and I don't know what that is, right? Then a3 is going to equal negative a0 times 1 over 3 times 2. Because if my subscript on my, like, what I'm trying to find is 3, what did that make my n in my pattern? 0. Perfect. Then a6 is going to equal negative a3 times 4 over 6 times 5. But we know what a3 is, right? We just found it. So if I substitute in what I have for a3, I get positive a0. And in the numerator, I have times 1 and times 4. All over 6 times 5 times 3 times 2. Okay. I'm going to write out one more so we can see the pattern. Now, this isn't going to be like the nicest pattern in the world in terms of like, we're not going to have factorials in it. That doesn't always happen, but we can still kind of write a general pattern. So a9 is going to be negative a6 times 7 over 8 times 9. But I know a6, so I substitute that in, and I get negative a0 times 1 times 4 times 7 over 8. Let's do that in a way that makes sense. 9, 8, 6, 5, 3, and 2. Now, these are all multiples of 3, right? The things on the left. So when I write my general pattern, I'm going to call this A sub 3n, right? Because what we're generally going to say is this is all multiples of 3. How do I get multiples of 3? It's 3 times a number. So for my pattern, I'm going to have negative 1, and then do I want it to the nth power or to the n minus 1 power? I want to start even or odd. Yeah, I want to start odd because I'm going to start at n equals 1. So I'm going to raise it to the nth power. And then what am I multiplying in the denominator or in the numerator? I'm multiplying 1, 4, 7. So the way I can write this generally is this is my multiple of 3 minus 2. Sorry, up to my multiple of 3 minus 2. I forgot some things. Sorry, it's 1 times 4, and then all the way up to my multiple of 3 minus 2. So this is just a general way of saying I'm going to count by threes and multiply up. We'll put it right here. Yeah, it's still there. Thank you for catching me. And then can anybody find a pattern to what's happening in the denominator? This one's harder. That is true. It is in factorial divided by what we have in the numerator. You could try to write it like that. I'm just going to be a little bit lazy, and I'm going to say this is 2 times 3. Then we skip 5, 6. So what we're doing is we're doing 2 things, skipping 1, 2 things, skipping 1. And what we have is, let's see, we have 3n minus 1 times 3n. Because if you look at, let's look at 9. When my subscript is 9, the second smallest thing I have is minus 1. And then the second biggest thing I have is minus 1. And the biggest thing I have is the same as the subscript. Excuse me. So we can find a pattern. Like there's not a nice like in factorial way to write this. This is as condensed as we can get it, but this is a fine way to demonstrate the pattern that you found. Because what we're eventually you just want enough of a pattern that we're gonna be able to write a general solution to this. All right, now we are going to look at our things that are multiples of 3 plus 1. So we have 1, and then we have 4, 7, etc. So the way I can generally write this is I have a 3n plus 1. That's the thing we are going to be looking for the pattern of. And in order to find this pattern, I'm just going to write out a couple terms. So a4 is negative a1 times 5 over 6 times 7. No, it is not. I'm looking at the wrong line. Okay, a4 is negative a1 2 times 3 times 4. That makes more sense. Then a7 is going to be negative a4 now times 5 over 6 times 7. But if I substitute in my a4, I'm going to get a1 times 2 times 5 over 3, 4, 6, 7. So let's see if we can utilize this to write a general rule for a3n plus 1. What's the first thing you guys think we want? Yeah, we need a negative 1 in there. We're going to do negative 1 to the n because we are starting with a negative. And then we have A1, because all these are going to have A1s in common. And then we have 2 and 5. So if I were to continue that pattern, it would probably be 2, 5, 8, 11, right? We're counting up by 2s. So the way I can write this is 2 times 5. And then the general thing is 3n minus 1. Notice, I think like this is a really interesting pattern we can notice. In our general rule, we had n plus 3 and then n plus 1, right? So that was 2 less than what I had on the left. So here, I've got this and then this. It's 2 less than what I have on the left. So that's where it comes from. And then this is going to be over some stuff. So we'll have 3 times 4, and then 6 times 7. And how can I like end this? Exactly, Sarah. 3n and 3n plus 1. So the last thing we have to consider, which is going to be our easiest, is what happens. We start with A2 and then we look at things with the form of A3n plus 2. But we already know what A2 is. A2 is 0. So what do you think is going to happen to all of these? Zero, right? They're all going to depend on A2. So let's write that first one just to like drive that point home. So we'd have A5, which would be negative A2 over or times 3 over 4 times 5. Because it has a 0, right? So then A8 is also going to have a 0 because it depends on A5, but A5 we've just decided is now 0. So that's why all of these have a 0. So let's see if we can now take our patterns and write a general solution, which we're going to be able to do. So we've got y equals A0 times the sum from n equals 1 to infinity, 1 to infinity of hold on. I'm trying to remember if it starts at 1. It does not start at 1. I apologize. It does, in fact, start at 0 because we want to get that constant term. I almost missed out on that. Okay. Of negative 1 to the n, 1, 4, all the way up to 3n minus 2 over 2, 3, 5, 6, all the way up to 3n minus 1 times 3n plus A1 times the sum from n equals 0 to infinity of I don't know if I said it out loud, but I know I wrote it. So I just want to like highlight that you should have an X in here as well. And it's an X to the N, so I didn't even write it correctly. So let's write that correctly. And then for our second one, we have A1 times the sum from n equals 0 to infinity of negative 1 to the n, 2, 5, dot, 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 3n minus 1 x to the n plus 1 all over 3, 4, 6, 7, 3n times 3n plus 1. Okay, why would I even care to go through the trouble of writing it this way? No idea? Not a clue? This feels like a lot of work for nothing? Fair enough. If I call this y1 and this y2, so it's everything but those constants out front, I've just found that y equals y0, y1 plus a1, y2. So for all these second order linear differential equations, haven't we been trying to find a constant times a function plus a constant times a function to make a fundamental set for this? For our differential equation? Yes, we have. That's been our goal, even if you have not realized that's been the goal. So, right, these A0 and A1 are acting like our C1 and C2 that we had before when we were doing, when you were finding the eigenvalues and stuff for those constant coefficients. So when you don't have constant coefficients, it gets a lot harder to solve these, right? So the last thing we want to check is we do, in fact, want to check if these form a fundamental set, right? Does this encompass all the forms of equations that satisfy this differential equation? So let's just remind ourselves of the following theorem. If you are given y1 and y2 that are solutions of something of the form y double prime plus px y prime plus qx y equal to 0, then y1 and y2 are a fundamental set of solutions. And by fundamental set, we just mean all solutions have this form. They form the entire solution base. If and only if the Wronskian does not equal 0. Throwing that Wronskian back at you. So this is going to be kind of difficult to check because we need derivatives normally, right? So I don't really know if I want to check these with these nasty y1s and y2s I just figured out. But we had this kind of extension that W is, or the Wronskian is always 0 or never 0. So we only need to check one point. And we can be judicious and check a fun point, a nice point that makes things cancel out. That's always the goal, right? Okay. So we want to check if our y1 and y2 form a fundamental set. So we are going to check for a fundamental set. Okay. So I'm going to look at y1 of 0, y1 prime of 0, y2 of 0, and y2 prime of 0. So this is what I meant by checking a nice point. 0 is probably going to make a lot of things cancel out, right? So if I look at y1, any ideas what y1 of 0 is going to be?
It's not defined. So for n bigger than 0, you're going to have a 0, which is going to cancel it all out, right? But at n equals 0, what does this become? 1. Good. And so we're going to have 1 times a bunch of stuff, but this n is 0, so we don't actually have as much as we think, right? So this entire thing, y0 is actually just 1. Because we're basically not getting any of those numbers that we threw in there. Yeah.
How does it work in the last term then? Like, we generally find it with 3n minus 2.
Mhm.
It's not. It's going backwards.
Well, 3n minus 2 is 1 in this case. Yeah. And then we actually don't get the 3n minus 1 or the 3n. So all goes away. Okay, let me think it through really quickly. Three, 0. Yeah. Down 0.
This one was
To set.
hence. Hence.
Sorry,
Like y1 of
that 0 is x, but when you plug in an x, a 0 for x, every single term is going to cancel out except n equals what? X, 0 to the first is 0, 0 to the second is 0, 0 to the third is 0. So the only thing that is not 0 is 0 to the 0 power. That's 1.
Again, 0 and then you get a 0.
Yeah. You also get the -2.
So when you use this notation, we're writing it to kind of try and combine it all. But if you get something that's undefined down here, that's just the first term, so we ignore it. Which I know is not fun. Yeah. So what we're basically saying is, remember from yesterday, right? If we wrote out a couple of terms, our first term is just a 0 plus a1. So this is really the term we're concerned about, is this a0 term, because it's a0 times x to the 0. So when we are writing the summation notation, we are being a little bit loosey-goosey in the terms of, like, for that first term, we just get a0, and that was the goal. And I know it looks nasty because you do technically get a 0 in the denominator, but for the purposes of being able to write a fundamental set here, here's what we'll do. Let's see if I can make this a little smaller and we'll adjust. So how we can think of this is we have y equals a0 times 1 plus all of this, and we can start it at 1. And this is our y1. So if I start the indexing, are we more happy with that now?
because I needed to pull out my first term. From there, and I factored out all the A zeros. Yeah. And then I think we would have to do the same thing for Y2. Let me think it through for just a second. Yeah, because you would get a 0 in the denominator, which is our problem. So we would have, let's see, where can I throw this in? We would have X plus all of that times A1. And then we would start our summation at 1. Thank you for calling me out on that. Mathematicians sometimes get a little lazy with their notation because they're like, we all know what I'm talking about, but you guys are learning, so you don't know what I'm talking about, right? So our Y1 would be 1 plus the sum starting at 1, so we don't get a 0 in the denominator. And then our Y2 would be X plus the sum, so we don't get a 0 in the denominator. But we start both of the summations at 1. Is that okay? Have I just confused the heck out of all of you? Pat is shaking his head. Thank you for being honest. Okay, but let's look at it. So since we are now starting at 1,
If I want to calculate Y1 of 0, if I plug a 0 into X for all of these, I get this whole thing becomes 0, right? So that's how I got the 1, okay?
if I want Y prime of 1, I would take the derivative and I would end up with a 0 because your constant term is going to go away and then the n in front is going to mess with things and make things 0. And then what's Y2 of 0 going to be? Plug in a 0 for X. What's Y2 of 0 going to be? 0. So if you look at
Y2, I'm going to plug in a 0 for all of these X's. Okay? If I take a derivative, let's just focus on this X. What's the derivative of this? So what's Y2 prime of 0 going to be? Yeah.
Y2, 0, 0. I thought it would be X. That's our first time.
but we're plugging in 0 for X. X is our independent variable and we're plugging in 0 for X. Okay.
What's the derivative of X? Okay. That's where it's from.
But X is 0.
But all these other terms are going to have an X. Yeah, so you're going to have 1 plus a bunch of X. So that X becomes is the only thing you have.
Okay. So my Wronskian is going to be the determinant of 1, 0, 0, 1, which is 1, which does not equal 0. So thus it forms a, I guess I should be more specific than it, thus Y1 and Y2 form a fundamental set. All right, we have 10 minutes. What I would like to do is I would like to go to boards and I would like you to attempt this pattern finding and determining if it forms a fundamental set that we just did. based on the problem that you guys did on the boards. Okay? Let's try that. Yep.